hooks are small, they can catch small fish. If the hooks are big, they can catch big fish. So if I've got big hooks, then Q would work as a large number for big fish, but for small fish, I would catch virtually nothing, except for the big fish, the biggest specimens of the small fish. So that's why Q is in there. If I compare for fish of different ages or boats of different kinds of technology or different kinds of species of fish. But I can always choose my units to make Q equal to 1 if I'm only dealing with one thing. So I can always scale my measurement of effort. So what I call a standard boat, if Q is 2, then I could just say, okay, standard boat is twice as big as a standard boat now, and then Q would be 1. So if I change my definition of what a standard boat is to twice what it used to be, and Q used to be 2, now Q would be 1. So I can just get rid of it. So it's got to do with the units, and it doesn't play a role in the detailed analysis. Okay, so I'm going to just switch this off now and use the code. So now we're going to look at that situation again. Here's f as a function of n, and here's n. And this is the logistic model. It's got a quadratic growth function. Now, it is possible to get other kinds of models. So, for example, I may have an asymmetric model. So in this case, the population growth is not symmetric. So this is not a logistic. It's kind of like a logistic model. It behaves almost like a logistic model, but it grows much more rapidly initially than it does kind of slow down after you get to the halfway point. So you can get to the halfway point very rapidly. So it's going to give you, you're going to have that skew. Now the other one is one that looks like this. And this is called a depensation, or a depensatory growth. And in depensatory growth, the growth rate initially is much slower than expected than in a logistic model, and is only vigorous when the population gets beyond a certain point. Now, what kind of phenomena might this describe? What sort of population do you think? What kind of underlying biological processes would lead to a growth that is super slow at low densities and only sort of speed up once the population gets beyond a critical point? So it's kind of the opposite of this. This may be that in the environment there's a small number of really good places to hang out and get lots of food. And so the first individuals in go to the good places and they grow more rapidly. And as you get more and more individuals and they spread out, if the environment is not homogeneous as they spread out, then individuals who come in later are getting worse and worse places to hang out and less food, so you get a situation like this. This is kind of the opposite. You do badly in small groups and you do better in larger groups. So what would that reflect? Yeah? Yeah, so what sort of things make you survive in a group? Yeah, social factors. Like wolves. Or if you're not a predator, then maybe you can have a more effective defense, like herds. So, if you're a few isolated individuals, you're much more vulnerable to a pack of wolves if you're prey. So that's possible. So this is depensation, and the other thing that you can get is critical depensation. So that's where the function f looks something like this. So it says that when you're below a critical level, even though you're not being harvested, this is just the natural growth rate, here you have an equilibrium which is unstable because the slope is positive. Here you have an equilibrium which is stable because it's negative, and here you have an equilibrium which is stable because it's negative. So this population looks something like this. If this is n, and this is time, you've got an equilibrium down here, you've got an equilibrium at 0, and you've got a carrying capacity. If you start close to here, you go to 0. If you start just above here, then you kind of grow logistically, and if you start above there, you come down to the carrying capacity. So the solution looks something like this. So this is thought to happen in populations where if they go below a critical level, they're no longer viable. And some people thought this may be the case with very large whales, that they've got to find mates. And if they're so rare, it's so difficult to find a mate, that the probability of reproducing when the density gets too low is now below a critical level, so they can't find mates effectively. It turns out that for the blue whale, people thought this might happen, but blue whales actually come back. And so new population levels of the blue whale are now much better than they were 30 or 40 years ago. Okay, but now let's have a look at the equation dn dt equals f of n, and h I'm going to call v times n. So let me do it over here on this one. So if I'm going to plot h equals v times n over here, then v times n is just a straight line through the origin. So that's v1 times n. And this is v2 times n. And this is v3 times n. And over here, we get v4 times n. So you can see that as I increase the value of v, I've got one equilibrium here. And if I look at this equilibrium, it's stable because if I'm above this point, v is larger than the growth rate. The red is larger than the black, so I'm heading down. If I'm below this point, the black is larger than the red, so the growth rate is larger than the harvest, so then I'm moving up. Now over here, this is going to be a stable equilibrium as long as the slope here gives me an equilibrium value. You'll see that in the case of v4, the slope is so steep that it doesn't intersect with the black curve. So what is the slope of the function f at the origin? It's df dn evaluated at n equal to 0. So if you look at this curve and you say, what is its slope at the origin, you can write this down. So in this case, v4 is greater than df dn, and df dn is greater than v3. Now if you have a look at the equilibria that arise when the red curve and the black curve intersect. That's the red curve. When they got the same value, then the NDT is 0, so that's an equilibrium. So these are all stable equilibria, but the stable equilibrium first starts out small, and it gets bigger and bigger until it gets to this point over here. And this point is called N, maximum sustainable yield. Now you'll see that in the notes, I've done this all with X, not with N. But if you read a lot of the fisheries textbooks, or some of like mathematical bioeconomic textbook, it'll be X. If you read other books, they'll use N. So just think about it as either N or X. Yeah. Yeah, so this is a stable equilibrium because above this point, the red curve is higher than the black curve, so you've got to go down because the red is bigger than the black, so it's negative. Below this, the black is still bigger than the red, so it's stable, but it's right at the edge. So now in order to get maximum sustainable yield, you have to choose V to go through this point that gives you the maximum. So this is H, maximum sustainable yield, and this is V, maximum sustainable yield, times N. So you get a maximum sustainable yield effort level. If you multiply it by N at the equilibrium, which is the N maximum sustainable yield, then you'll get the maximum sustainable harvest. So the point where the harvest is maximized is the value of V that when it intersects with this curve, intersects right at the top. Now what do you notice here? Unlike H, if you increase V, you don't go to an unstable situation. You still have so if you miscalculate things and you make V a little too big, and you're over here, you're still at a sustainable point that's stable. But if you go back to what we were saying over here, if you get H wrong just by a smaller amount, then you've lost your sustainability. Over here, if you get V wrong by a small amount, then you haven't lost your sustainability. So this is much more robust. So that's why when you regulate, say, a fishery, instead of saying we're going to limit you to 25,000 animals per year, you should say we're going to limit the amount of effort you can put in. And that's because it's a natural feedback. If you've got a fixed effort, then for that fixed effort, as the population gets more and more rare, so the number of individuals you can catch for that fixed effort goes down. So there's an automatic feedback on your catch rate or your harvest rate. Does everybody understand that? Okay. So now, the last thing that I'm going to talk about is that if you want to harvest a population and you want to set the effort level that will give you maximum sustainable yield for all time, you've got to say, well, that's okay, but I don't start out at this level. I don't start out in an equilibrium situation. So what should I do? How should I regulate the fishery in order to maximize the harvest at this point in time? So it turns out that if you are above the maximum sustainable yield level, if I'm over here, I'm above NMSY, I can have a greater harvesting rate than VMSY as I drive the population down. As I drive the population down, once I get to this point, I better switch to the effort level that gives me maximum sustainable yield, because if the effort level is higher than that, in other words, if this is greater than VMSY when I get to NMSY, then this is going to be larger and the population is still going to continue to decrease. So what I can do is I can specify that you can take more out of a fishery at a point where it's not yet been exploited to the maximum sustainable yield level. It's as though in any renewable resource, when you come to it, it's unexploited. And the level at which you can exploit it sustainably to get the maximum sustainable yield over time is that the population is below its carrying capacity. In the case of the logistic model, the population is sustained at half its carrying capacity because that's where it maximizes its growth rate. So if you come to a population that's over here, you have all this excess resource in there that you can take out. And if you're doing a present value calculation, your best strategy is to take it out as rapidly as possible. Now, when I say take it out as rapidly as possible, it doesn't make sense to go and buy a whole bunch of boats so that you can harvest as rapidly as possible, because once you get to this point over here, you're now going to have to cut the number of boats down to the level that's sustainable. So you don't want to overcapitalize because now you've got these boats and you're going to have to sell them. So you can do a calculation that helps you decide what to do. And what you should do depends very much on what happens when you get to maximum sustainable level if you've got some boats. Can you switch some of the boats to an alternative fishery? Can you sell them easily? Can you scrap them? So all those answers go into deciding what the optimal strategy is. But then there's the opposite side of that. And let's say we come to a fishery and we can say for years and years and years, we've really been very bad. We've totally overexploited this fishery. This fishery is sitting down here. And it should be up there if we're going to maximize yield. It's sitting down here. How do we get it up to here as rapidly as possible? To get it here as rapidly as possible is to have V equal to 0. Let it rise as rapidly as possible. Then it rises as rapidly as possible, and then you can say, okay, when we hit this, now you can start to harvest. The problem with that is, if I stop fishing and I wait a couple of years, then what do I do in those 2 years? How do I get revenue? I can't say I'm going to maximize over a 20-year horizon, but in the first 2 years I earn nothing, and then in years 3 to 18 I earn more than if I didn't earn nothing now, and I say had some small rate at which I was taking out. So because you might not be able to sit out the 2 years. So it comes to some compromise. So this is always the case when you rebuild fishery stocks. If the fishery scientists say the best way to harvest this in the long run is not to harvest it until it's recovered to this level and then to start harvesting at the maximum sustainable yield level, that's okay if there are alternative resources I can exploit in the meantime. But if there aren't alternative resources that I can exploit in the meantime, then some solution has to take into account the fact that I have to get a certain amount of revenue. Now, if the government can take a long-term view, then they can subsidize individuals and they can say, we're going to pay you not to fish for 2 years. And in agricultural policy, this is exactly what happens in the US. We pay farmers not to grow things. And the reason why we do that is because those farmers help to elect the senators who vote for those policies. It's not good for the US, but it's good for the senator. Have you ever noticed that senators never do what's good for the US? They only do what's good for themselves, which by implication is for the very wealthy people in their states who give them money to be able to effectively run their campaigns. So Anyway, so resource policy turns out to be quite complicated. But in order to understand the basics of the biological side, we have these kinds of models. And then we start to put in some more of the economic considerations by adding discounting and cost and that sort of thing. And when we combine those ideas together, we get what is known as bioeconomic theory, because it's got economic elements, it's got biological elements. And so on Thursday, we'll talk a little bit about very simple bioeconomic models and ideas. Okay, thanks.